Today we got a warm up, and then we have notes today on section 4. Yeah. I have a circle's diameter, so that long line passes through the middle of the circle C, and I've indicated a couple lengths on there for this diameter, which bisects a chord. Half of that bisected chord length is 12, and the distance from the center of the circle to the chord is 5. Please solve for x and the exact value of the circumference of the circle, or maybe do the circumference first, well, whatever is easiest for you. After that, we'll go through it, and then today we'll have a pretty important lecture. Today we'll be talking about an idea called inscribed angles and polygons. This is a big, you know what, I'm not going to say it's a big topic on the SAT, but this is definitely one of the newer topics on the SAT, like it was added within the last, I think, 7 or 8 years. And so if you happen to get one of these questions, then this section right here is the difference between getting that perfect 800 or, you know, happening to miss one on the SAT, having it be this like weird topic. Trying to find the sample SAT that I wanted to refer to before we start. I want to show you guys the question that comes out of this section. Have you guys started your own SAT prep yet?
Yeah. But I do more ACT than SAT.
Yeah, same practice effectively. Now is about the time that you should be starting that process. And know that if you do begin practice, I mean, don't get me wrong, take a week off for yourself. Like, go chill, go play some video games, or binge whatever thing on Netflix you could do. I would normally suggest healthier hobbies like hiking and exercising, but you know, social distancing, blah, blah, blah. Anyway, when school ends, take some time off for yourself, right? And then when you get back to it over the summer, it's important to like not let your mind atrophy. This would be about the time that you want to start doing SAT prep. Either sign up for the stuff that they put out through the through Khan Academy. That stuff's all really good if you want some help getting started. And know that you won't know all of the math topics that are on there yet. At this point in your like math career, you'll know most of them. It only covers math up through part of Algebra 2. So after the first few months of next year, you'll have all the math that you really do need to do well on that test. But the test itself and doing well on it is more about practice and repetition than it is about real skills. And the sooner you start your practice and repetition, the higher your final score will be. And on the College Board, if you type in free practice SATs, they have like 10 full-length practice tests with answers. So there's plenty of practice available. It's just a matter of taking the time and the energy to get it done. Anyway, let's go ahead and get started. What is this question actually asking about?
To use Pythagorean theorem to find the radius.
And the Pythagorean theorem only applies when we have a right triangle. So where's my right triangle?
It's on the right where you have like that 5 and the 12 where the diameter is bisecting the chord.
Correct. We have a hard and fast rule that if a diameter bisects a chord, they must make a 90-degree angle because of the properties of circles. For more details on that, of course, go back to the previous section's lecture. But nonetheless, that allows us to do the Pythagorean theorem to get this. And when you do the Pythagorean theorem on 5 and 12, we get that 5 squared plus 12 squared is equal to, I'll just say that this is r, because this is clearly the radius, right? It goes from here to the edge, is equal to r squared. And what do you get for r?
It has to be 13. It's a Pythagorean triple.
Yeah, 5 squared is 25, 12 squared is 144, 25 plus 144 is 169. Square root of 169 is 13, so we get a Pythagorean triple. So that means that this circle has a definite radius of 13 if these two measurements are correct. But what does that have to do with x?
can't we add, we know the radius and we know the diameter, so can't we add the radius plus 5 plus x equals the diameter?
That is a true statement, but that's one equation with two variables, and as such, it cannot be solved. It's even,
Oh my
you're
God.
overthinking
I
it.
did-
X, you can do 13 minus 5 because that's a
I
radius.
did not think
There
of
we
that.
go. And that is the key. And again, man, I'm telling y'all, this circle stuff is hard because it's so easy. The thing that you have to keep in mind, and your brain should go here immediately whenever you think you're stuck in a question, every radius in a circle is the same, whether or not it's drawn in or labeled. So the Pythagorean theorem gives us one radius, but Maria, explain it to me one more time.
So if the radius is 13 and 5 plus x is 13, then just do minus 5.
Precisely. If one of these radii is 13, they're all 13. So we got from over here, the Pythagorean theorem tells us that radius is 13. And this here is also a radius, even though it's not super obvious, but that means 5 plus x is equal to 13. So x is equal to 13 minus 5, which is?
8.
That's a great warm-up. And that's the that's the hard part. That one comes first. And so what is the exact value of the circumference in this case?
It's pi.
26 pi.
Oh, yeah.
Yep, 26 pi or pi 26, both good.
Does that say r equals 13 and 5? Or what is that? That you...
R is equal to 13 and 5 plus x is equal to 13.
Oh, okay. Yeah.
Which I guess a better way to say this is actually r is 13 from this first part and 5 plus x is equal to r. Yeah, and then transitive property is what gives us x equals 8. Anyway, that's a good question that is straightforward mathematically, but a little bit tricky to get down conceptually. Anyway, today we're going to talk about 10.4, which is called the Inscribed Angle theorem. And I've done my best this year to red flag out topics that I have seen on the SAT in recent years, because that's usually a good indicator of what they're going to keep doing. So just a quick warning, inscribed angles are on the SAT. I have seen them in my work tutoring the juniors and giving them SAT assignments. They often show up in the free response section. So let's start off with definitions, and then of course, and by the way that these math lectures look now, where these lectures are almost always after the warm-up, we do a definition and then a proof, right? And always keep in mind, the proof is separate from how we use this information to solve problems, but nonetheless, the proof is where this data comes from, which is very important if you want to understand how to manipulate this stuff to solve real-life problems. So this proof that we'll be doing at the top, it's not how we solve these problems, but it is going to lead us to a very, very useful equation that we will be using for the rest of the section. An inscribed angle is an angle inscribed angles are formed by the intersection of two chords on the edge of a circle. And you're like, that's boring. Why would you define that? Who cares? I'll show you. Those of you naysaying freshmen out there, I know who are naysaying. We'll put down the circle. Ooh, I didn't ruin it this time. Hopefully I didn't speak too soon. Hey, a nice clean circle. I didn't change size as I went. I'm going to label the center. Not because it's part of this definition, but because we will need the center of the circle labeled in a moment. So the center of this circle is circle D. And an inscribed angle is technically any angle which is formed by two chords which intersect, and they have to intersect on the edge of the circle. So here are my chords, here to here. there to there. And I'm going to call this A, B, C. And believe it or not, there are actually some pretty interesting statements we can make about what is going on here. However, the way in which this is going to be achieved isn't very obvious based on the way that this is drawn. So just so you know, what we're about to work towards is called the inscribed angle theorem. And we'll box it at the bottom. Well, let's go ahead and see if we can work it out together for the sake of our SAT scores. What's that piece of advice that I'm always giving you guys about solving circle questions? If there doesn't seem to be enough information to do something, what do? What's a good approach?
Use the radius or find the radius.
Yeah, use radii, and keep in mind all of the radii have the same length, even if they haven't been drawn in yet, which means that either you need to draw them in your mind's eye, or when your brain isn't sufficient, bust out a pencil. I'm going to do it in pencil just in case they aren't the ones that I want, so I can go back and erase them. So where could I draw in some radii?
DA, DC, DB.
DA, DB, DC. That I could add in 3 new radii here, and that would let us talk about the inscribed angle. And by the way, just so we know, the inscribed angle here by definition is inscribed angle ABC. So this is the guy right here who I am defining. I'll do this in red just so that we know that this mark is separate from everything else. So my goal in this long explanation here is so that maybe we can say something cool about the measurement of angle ABC. Oh, right, sorry, I totally forgot. I'm adding radii. So I'm going to add those 3 radii. And like I said, for no reason other than the fact that it's just good advice. And since each one of these is the radius, how should I mark them?
Put like a line
With the
on each one.
yeah, the congruent symbol.
Beautiful, with a congruent symbol, just so that I can know that they're all equal without me having to draw anything on here. And oh, hey, what would you know? I formed 2 whats?
Triangles.
Be more specific. They are
Mm.
triangles, but what kind?
Right triangle.
Oblique. Or,
Isosceles.
That's the one. They're both isosceles.
Oh, yeah.
Both of these have 2 sides which are congruent, which means that their corresponding base angles themselves, well, those must also be congruent. So I'm going to make some congruence marks in here using my regular old black pen. So that is to say that this angle right there is congruent to this angle right here. Oh, heck, no, don't look at that. It's wrong and bad. I got too excited. This angle right here is congruent to this angle right here. And this angle right here is congruent to this angle right there. So I'm going to give each one of these a variable. I'm going to call this angle x, and I'm going to call this angle x logically. And then this angle here, I'm going to call y. So this angle here must also be y. That's just logical. Is that okay?
yeah.
Yeah.
Is this okay? Okay. So here's why I am doing this. What have I redefined our inscribed angle as? How could I rewrite it with
Y plus X.
Very good. Notice this original inscribed angle, angle ABC, that's still this angle, the one I drew in pen. And that's just angle X plus angle Y now. So this is going to be equal to X plus Y. Now, if we could redefine X and Y using some of the other values here, then I might be able to write some sort of statement of equivalence for this inscribed angle. So now let's go ahead and take advantage of the following hieroglyphic recipe. Could I get somebody to read the hieroglyphics here?
Triangle hieroglyphic theorem, or wait, what was that?
Angle sum theorem.
Oh yeah.
the triangle angle sum theorem. And what does this tell us about any given triangle?
What it adds up to?
Which is
180.
correct. No matter what, all of the angles have to add up to 180. So for both of these, I have x and some unknown angle. I have y and some unknown angle. So I'm going to go ahead and I'm going to redefine these two unknown angles up top. So these two unknown angles up here, well, if I'm saying that x plus angle BDC, these have to add up to 180 degrees. So now I can get angle BDC by saying that angle BDC has to be equal to 180 degrees minus, what is this?
X squared. X squared.
2x.
2x.
Oh,
X plus x
forgot.
is 2x, x times x is x squared. But yeah, this
my
is
bad.
2x plus angle BDC. So to get BDC alone, I subtract 2x over to the other side. So that means that this angle right here, angle BDC, that has to be 180 less 2x. I'm going to go ahead and I'm going to add those as well. So this is 180 minus 2x. But this right here, what would that have to be? Follow the same logic. This is a triangle.
180 minus 2y.
Wonderful. So this is 180 minus 2y. I'm going to rewrite that a little bit bigger. I think that's hard to see. Sorry about that. If it was the smartboard, man, I could just like pinch and zoom it and make it bigger. I miss the smartboard. Is that okay? 180 minus 2y?
Yeah.
Yeah?
Mm-hmm.
Yeah.
And so up here, we have this angle. What is that angle called?
That's the angle measure, I think. The
You're
arc
very
measure.
That's the one. It's the arc measure. So notice this other angle right here, we could equally call this the arc measure of AC. And what do all of the angles in a circle add up to?
360.
Yeah, they should add up to 360 in total. So here's what I'm saying. This piece of the angle, that's 180 minus 2x. This piece of the angle, that's 180 minus 2y. And this right here is the arc measurement of AC. And in total, these three make a complete circle, right? This piece and this piece, plus that missing arc measure. They make a full circle. So I can say that 360 degrees is equal to 180 minus 2y plus 180 minus 2x plus the arc measurement of the arc measurement of AC. Three angles making a complete circle. Is that okay?
Yes.
Now let's do some spicy algebra. What's 180 plus 180?
360.
So I have 360 is equal to 360 minus 2x minus 2y plus the measurement of arc AC. Now what should I do?
Minus 360.
I'm going to subtract 360 from each side. They both have 360. So what's 360 minus 360?
0.
0.
0 is equal to negative 2x minus 2y. Yeah?
Yeah.
Yep.
And I don't like negatives. So how can I make those all positive?
Divide by -1.
That would make the
That's
measurement of
figure
arc
out.
AC negative. I want
Factor
everything
out
to
the
be positive.
negative.
That's not valid math.
It'll do the same
Oh,
thing.
you do 1 over negative 2x? Or no?
Positive divided by a negative is still negative. I want to make this an equation where everything is positive. Take it one piece at a time. How can I make it so that the x part was positive?
Divide by -2x.
That would make AC negative.
Multiply by -2.
That would make AC negative.
C negative. Okay. Oh, add 2.
Yep, y'all are overthinking it. Add 2x.
Wow.
If I add 2x to each side, it'll cancel out this 2x, and I'll get 2x I'm going to also add 2y. 2x plus 2y is equal to measurement of arc AC. And now I'm going to factor out a 2 here. 2 times x plus y is equal to measurement of arc AC. But wait a minute, x plus y, that looks familiar.
That's
means
the
angle B.
angle
That angle B.
of ABC.
Wow.
And that's exactly what the inscribed angle theorem is talking about. That is the exact statement. So this next line that I'm about to write, this is actually the equation that you use to solve problems. This is all just the very complex logic that we go through in order to establish this theorem. I just didn't want to give you guys the answer. That's no good. So here's the final statement. 2 times x plus y, which is the same as saying 2 times our inscribed angle, A, B, C. Oh, heck, I forgot my angle symbol. 2 times angle measurement A, B, C is always precisely equal to the measurement of arc AC. This is to say, the measurement of an intercepted angle, and one more time I'm going to outline that intercepted angle. Intercepted angle is right there, is always exactly 1/2 of the measurement of the intercepted arc. So arc AC goes from here to here. That angle that I'm talking about being formed here in the middle. Because of these fancy properties going on within circles, if you have an intercepted arc, an intercepted angle, look at the arc that it intercepts on the opposite side, and this number must be exactly 1/2 of this number.
So if we were told that ABC was 30, then the arc measure of AC would be 60.
Can you say that one more time for me?
If we were told that angle ABC was 30, does that mean that measure of arc AC is 60?
Yes, if this is 30, this is 60. In this case, this seems to be probably 60-ish, so this is probably 120-ish. And actually, because I drew this with a ruler using the real center of the circle, this should work. And y'all saw me draw this live, right? So y'all know there's no trickery here. The measurement of this intercepted angle seems to be 71 or 72 degrees. See that right here, the 70 just over?
Yeah.
So that means this
So
should be
be 140, like something.
let me make sure I got it. Yeah, it was about 72, so this is coming up on about 144. Yeah.
Yeah.
Is that okay?
Yeah.
Wild. So like I said, this is the proof. This is the thing. I think this is a mess. It is a mess. That is just to explain where this idea comes from and why we're engaging with it. So let me redraw it nice and clean. So the inscribed angle theorem . And this is just the bits and pieces that you need to solve problems. Here is the stripped down version of the inscribed angle theorem. I have 2 chords which intersect on the edge of a circle. This produces an intercepted angle, and this intercepted angle has a special feature. So long as this right here is some value x, if we go out and we intercept these 2 points, A and B, 2x is equal to the measurement of arc AB. But it's important to keep in mind that the definition of an intercepted arc is that it is the angle that that arc would make should you draw in its 2 radii with the center, which means that this angle here in the middle is 2x. Because circles are fancy, if you set up this Star Trek logo inside of a circle, it will always be set up such that this angle doubled gives you this angle. Is this okay?
Yeah.
Tight. Yeah, and like I said, I have seen questions on the SAT where it's a circle with some lines drawn in it or whatever, and without this piece of trivia in your head, you can't work the question because you got to admit, if I showed you this without explaining why first, where does that come from, right? Isn't that wild? This is one of my favorite like proofs of the year, I think.
Is this like the last proof?
Oh, no. The proofs never end. And even once the proofs end in geometry, that's just a opportunity for the proofs in Algebra 2 to begin.
I meant in like this class. Is this like the last proof we're gonna learn? Or are there more?
No, there's still, so this is section 4. So that means at the beginning of next week, we have our last quiz. And then after that, I have 3 more sections on circles. And one of them has a proof. So this is second from the end.
So which day is our quiz?
I have the OWS written out for weeks in advance. I would check there. It's either Monday or Tuesday.
Okay.
Oh, it's Tuesday because we don't have school on Monday, I'm pretty sure.
Yeah.
Oh, you're right. Yeah, it's
Ooh, yeah.
Memorial Day on Monday. Yeah, so no school on Monday, quiz on Tuesday.
Oh, Mr. Robinson, are we going to do area of sectors or no?
Sector area is one of the last topics of the chapter, yeah, but it's boring. It's the same
Yeah,
thing.
it's really boring.
It's really boring, yeah. Okay, so past this, I have 2 special cases that I want to key you guys into. 2 special uses of the inscribed angle theorem. And again, these are special cases which can show up on the SAT. And here are the 2 special cases. Special case 1. A triangle inscribed with a diameter. Special case number 1 of questions about inscribed angles. Let's go ahead and say that I have a circle inscribed, and you know what? Just to keep the notes a little different looking, I'll put the circle on the right. That's not illegal. And now I'm going to go ahead and draw in a diameter. And can somebody give me the definition of a diameter that uses the word chord? A diameter is the
Longest chord in a circle.
excellent longest chord in a circle. And what I'm saying is that when you form a triangle by inscribing it and having it intercept the endpoints of a diameter, we're going to get a special case that we can talk about mathematically here. So I'm going to go ahead and I'm going to draw in a line, and I'm going to draw in another line. And so let's go ahead and figure out what this means. And to talk about this, I'm going to say that the center of the circle is D. This is a diameter A, B, C. And so what is special? I'll give you guys a second to think about it. Okay, so of course this is talking about our inscribed angle right here. This is our inscribed angle. And so the inscribed angle goes out and it's going to intercept a chord, right? This chord is AB, but because this is a diameter, what is the arc measurement of chord AB?
180.
What does the inscribed angle theorem tell us to do with this angle measurement to get our inscribed angle?
Multiply it by half.
And so what's half of 180?
90.
This is a right triangle. It must be. And again, all I'm saying here is that 2 times the measurement of the intercepted angle, angle ACB, 2 times that number is equal to the measurement of arc AB. This is just the inscribed angle theorem. But if this is a diameter, this flat line makes an angle of 180 degrees. Take 180 degrees, chop it in half, and that tells you that this has to be 90. Every single triangle which is inscribed within a circle and has a diameter as one of its sides, it must be a right triangle. And that means that if it is a right triangle, what special relationship works here? What special relationship works for right triangles that doesn't work for other triangles?
Pythagorean theorem.
It opens the door to the Pythagorean theorem. So even without knowing that this was a 90-degree angle, right? If this wasn't labeled, but all you were told is that this is a triangle inscribed within a diameter, then to be told that this chord length is 5 and this chord length is 12, that is sufficient information to establish that the diameter is 13. Is this okay?
Yes.
And here's an additional wrinkle to this that I always like showing, right? This means that no matter what angle you draw on the other side, so long as it inscribes this diameter, they're all going to be 90 degrees, right? And that seems unnatural until you see it, but check this out. 2, 3, 4, 5, 6. Every single one of these points will make a perfect right angle.
So is the inscribed, what's the inscribed angle? Like if it asks for it, which one is it?
The inscribed angle is the angle formed by the intersection of two chords at the edge of a circle.
Okay.
Where two chords meet at the edge of a circle, that point will form an inscribed angle. So here I've connected A to all of these points, and now I'm going to connect the other side of this diameter B to all of these points. And what do you notice about every single one of these angles? It's one of those things where it's oddly satisfying to look at least it is in my opinion. What do y'all see there?
So all of those are right triangles?
90, 90, 90, 90, 90, 90, all of them. No matter what triangle you draw, if it's inscribed within a circle and it intercepts a diameter, it is going to form all right angles. This one I believe is very special. I think this is very cool. This property is also allows you to do differential geometry using calculus within circles. This is an important one to think of. Don't get me wrong, they'll remind you about this in calculus, but this property comes up in calculus. Super useful property. Any questions here? Number one? No? We're ready for the second special case?
Yeah.
And this second case is special. It's not that special. That's why it's special case 2 and not special case 1. Special case 2. Any quadrilateral inscribed within a diameter. I'm sorry, not within a diameter. Any quadrilateral, any quadrilateral inscribed within a circle. So to draw this one, I have to take a circle. And how many corners does a quadrilateral have?
4.
Okay, so I'm going to pick 4 points, and to make the point, I'm going to make sure it's not special, not a parallelogram or any other specially related quadrilateral, something funky looking, kind of a quote-unquote scalene, even though technically that word only applies to triangles. So now I'm going to go ahead and I'm going to draw in my 4 sides. And then I'm going to attempt to make a copy of this. Again, if school was normal and we were in class, and I would just use the smartboard to literally do a quick copy paste. But I'm just going to do my best job here. I didn't adjust the settings on the compass, so that's good. And then I'm going to kind of use a ruler to make sure that these kind of go straight across here. Doot. 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 And then, hey, you, right here, right there. Is that okay? Can we accept that these are basically identical?
Yeah.
Okay.
Mm-hmm.
And so, here's what we're here to talk about. The statement that we're going to make here about a quadrilateral inscribed within a circle is actually a special property about the opposite corners of such a quadrilateral. So let's go ahead and consider first opposite pair here, AB. And then over here, I want to consider opposite angle pair CD. Is this okay?
Mm-hmm.
Okay.
Yeah.
So first, let's go ahead and look at angle A, and I'm going to highlight the arc that it intercepts. So if I trace these lines out here, A to here and here, then it intercepts most of the circle. So angle A here intercepts all of the arc that goes from here to there. Is that okay?
Yep.
Yeah.
And here's why I'm interested in its opposite angle pair B. Trace those lines from angle B out to here, out to here and here. Notice it intercepts this arc. What do you notice about that blue arc and the yellow arc?
The
360.
yellow arc takes more.
The yellow arc does take more, but what is their sum? I think I heard it out there.
360.
In total, angle A and angle B, they inscribe the whole circle. So I'm going to go ahead and write down an equation that describes that. So this is to say that 2A plus 2B, well, that inscribes the whole circle, so that's got to be equal to 360. What happens if I take this equation and I divide both sides by 2?
A plus B equals 180 degrees.
And here's why I make 2 copies of this diagram. Do the same thing for the perspective of angles C and D. So that is to say, if I start at C and I trace its chords out to here and here, that is to say, angle C intercepts this whole arc. And then if I call angle D yellow and I trace its chords out, it intercepts this arc from here to here. And again, what do you notice about those 2 arcs? What do they add up to?
360.
360.
So this is to,
Diameter.
yes. Huh?
Because like if there was a line there, it would be the diameter. It's like 180 and 180, right?
No. So just because 2 things add up to 360 doesn't mean that each one is necessarily 180. You could also achieve this by saying one is 350 and the other one is 10.
No, but it's like exactly in half. That this one, the blue and yellow one. I mean, on the right.
Oh, if that is the case, then it's not on purpose. It's merely coincidental.
Oh.
This is not a statement about what any one of these angles is. There's not enough information here to state that, because notice over here it's still true, even though the blue chord is very much shorter than the yellow chord.
Yeah.
We can only make statements about their sum. We can't make statements about them individually. If this appears to be half and half, coincidence. So yeah, this is to say that 2C plus 2D is equal to 360. And again, I divide both sides by 2 to say angle C plus angle D is equal to 180. And so let's go ahead.
How do you
Yes?
know A and like the 2A plus 2B is 360? Like, how did you come to that conclusion? Is that just how it is?
This whole section is about the inscribed angle theorem, which we derived in the first part. So a quick reminder about the inscribed angle theorem is that the inscribed angle theorem tells me that whatever angle this measure is, my inscribed angle, then the arc measurement on the opposite side has to be exactly double that. Why this right here is complicated. However, this is a direct application of that rule. So if this is A, this arc measurement must be 2A. If this is B, this arc measurement must be 2B. And if those arcs are sufficient to make a full ring, then it adds up to the whole circle.
Oh, okay, I get it now.
No, it's an excellent question. This is a hard one to pick up because I don't notate this one as clearly. The trick comes from the fact that if this is B, and I'll add it on here, that this is 2B from here to here, and that this is 2A from there to there. Good. And so now that we have this rule, and we've shown that it's the same over here, that if this is C, this is 2C, and that if this is D, this is 2D. We can now find a commonality between these two ways of looking at this problem. And I'll go ahead and start it off. And this doesn't really have a great name to it, even though this is probably a valid theorem, but it's a rule which is derivative of the inscribed angle theorem. If a quadrilateral is inscribed within a circle, so this is the conditional part of the statement, right? That's what's going on here. I have a a quadrilateral that I've trapped within the confines of a circle. So if a quadrilateral is inscribed within a circle, then let's go ahead and eloquently sum this up with our best geometry vocab. How would you describe the position of these angles here?
Opposite from one another.
Then opposite angles, and that's not ambiguous, right? Because there are exactly 4 angles, they come in exactly 2 sets of pairs. So saying opposite angles is only describing 2 pieces of information within this. So then opposite angles are, what is that? We have a word for this equation.
Supplementary.
Wonderful. In any case where you have a quadrilateral inscribed within a circle, then that quadrilateral will have a feature that we've never seen of general quadrilaterals, but opposite angles are supplementary. Oh, somebody's popular. Anyway, that is it for our notes today on the inscribed angle theorem and these special cases. To cap it off today, since we still have a little bit of time, let me give y'all 2 quick and easy examples just for those of y'all who need to see digits tied to this. Let's do a couple simple questions with straightforward digitry, numbers, number questions.
Mr. Robinson,
Yes.
something flew into my right eye, and I can't see out of it.
I'm
Should
not
I
a,
go?
yeah, go.
Okay, I'll be back.
Yeah, I'm not a doctor. I can't give medical advice, but yeah, go get whatever's in your eye out of your eye, probably with water. Okay, so item number 1, I have a quadrilateral inscribed within this circle. Please solve for x and y. And again, this is both just so that y'all can see what I mean here with numbers, but also we're going to verify it a couple different ways. And it's also going to act a little bit as an experiment here, where I'm betting whether or not what I've said this lecture is correct. Because since those are the actual angles that you saw me measure just now, then we should be able to verify whether or not these statements are correct by taking a direct measurement of these other 2 angles, right? Science is you make a hypothesis and you conduct an experiment, and if your hypothesis comes back correct, you know you're on the right track. And then in item number 2 here, the center of the circle is C. So I'm going to throw down this here diameter. And then I'm going to put a point on this circle. And here I'm going to give y'all two lengths. So the length of the hypotenuse here seems to be about 5.9 centimeters. And this short length here, the short line of that triangle, is appears to be 3.1 centimeters. This chord length, I should say, 3.1. And so here's what I would like to know. Please give me angle theta. What is angle theta equal to? Take a few minutes to solve for all three of these angles, which is only made possible by the inscribed angle theorem. And then we'll test with a protractor to see if these measurements are actually real or if I've been lying to you for the last 50 minutes.
Mr. Robinson, can't you just do the second part with the law of like cosines?
No, to do the law of cosines, you need three pieces of information. That's true of the law of sines or regular trig in general. You need to be given three numbers. I've only technically given you two numbers.
Oh, okay. But can't you assume that, never mind.
I mean, we don't make assumptions in math. The only assumptions we make are that 1 + 1 is 2 and that anything times 0 is 0. Past that, everything else we can prove out on first principle. No, you can know what this is, and it has everything to do with the fact that point C is the center of the circle. Okay. I have caught up on my group chat memes. Let's go through this. Item number 1. This is a pretty straightforward application of a rule. So what does angle X have to be?
115.
Yeah.
And what does angle Y have to be?
68.
Good. Nice and easy application of the fact that if there's a quadrilateral in a circle, opposite corners have to add up to 180. So these two add up to 180, these two add up to 180. Here's another reason why this is nice. As we know by the polygon angle sum theorem, n minus 2 times 180 is going to be equal to the total angle measurements inside. So what do all the angles in a circle have to, or in a quadrilateral have to add up to?
360.
Yeah, n minus 2 times 180 would tell us 4 minus 2 times 180 is 360. So if these pair off as 180 and these pair off as 180, then those two rules will always be in agreement. So let's see if we're correct. So first, here's angle Y. Line it up and then trace out its length. Oh, sorry. I guess my measurement on the other side was a little bit off. The measure Y here is about 70 degrees. It's a little bit off. That means I probably measured 112 a little bit wrong. But that one's pretty close. And then angle X up top. It happens to go up and split the difference between 120 and 110. See that side come out here, right between 120 and 110 for 115. What about this one? How could you possibly get theta given two lengths?
Trigonometry.
Trigonometry. However, trigonometry of the SOHCAHTOA variety only works for what kind of triangle?
A right triangle.
Right triangle.
Which this
Is that the case here?
This is.
Yes.
How do you know?
Because since the arc measurement that is opposite of the inscribed angle is 180, that means the inscribed angle has to be 90, meaning that that's a right triangle.
Right, so it's a right triangle, which means we don't have to do the law of sines or the law of cosines. We get to use the much easier methods of SO, CA, TOA. So with respect to this angle, what is this side length called?
Adjacent.
And what is that side length called?
Hypotenuse.
Hypotenuse.
So cosine.
Cosine is the ratio in SO, CA, TOA. That will give us what we want. CA is CAH. Cosine is equal to adjacent divided by hypotenuse. So this is to say that cosine of the angle theta is going to be equal to adjacent 3.1 divided by hypotenuse 5.9, which is to say that theta should be equal to inverse cosine of 3.1 divided by 5.9. And when you do that calculation, what are you getting out there?
58.30.
Yeah.
Yep, 58.30. And again, if this stuff is not a lie, then I should be able to verify that independently with my protractor, assuming the circle is good and that I measured these lengths more or less correct. And you'll notice here, after I get my protractor properly set, the angle comes in just under 60, about 58 degrees. And so, a quick recap of what we talked about today. It's a lot of stuff, but it's actually just one equation. So the one equation we talked about today is the inscribed angle theorem. If I have an inscribed angle at the edge of a circle, this angle measurement is exactly 1/2 of the measurement of the arc it intercepts. It is a comparator of this number being exactly 1/2 of this number. Where this comes from is very interesting. This comes from isosceles triangles mixed with saying that a circle adds up to 360 in total, and two clever substitutions. I'm never going to test on this part. This is just where it comes from, so it's in your notebook in case you ever want to go over it. And when we take this and we apply it, we get two special cases. Number one, if we inscribe something against a diameter, it's going to be 90 degrees, right? The arc measure of a diameter is 180. Half of 180 is 90. So if a triangle is inside of a circle and one side length is the diameter, well, that triangle must be a right triangle and trigonometry becomes possible. Special case number two, if I have a quadrilateral which is inscribed within a circle, because of reasons of algebra, the opposite angles of the quadrilateral must be supplementary. And with these three new rules in hand, this opens up a door to some geometric questions that we wouldn't be able to answer otherwise, particularly ones that can appear on the SAT. Are there any questions on today's lesson?
No.
No? Okay. Well then, I'm going to post the homework and I'm going to go downstairs and I'm going to drain some broth that I left boiling overnight, and I hope it's delicious. You all have a nice day, and I'll see you on Friday so that we can go over the current homework assignment, and I'll also lay out what the quiz will look like on Tuesday. See you then.
Thank
Mr.
you.
Robinson.
See you.
Peace.
Bye. Thank you.